Hey, this is me. I've recorded a second version of the 6.0 Homework 16 Applications of Quadratic Functions video this 2021 October, about a year after I did the first one. The biggest difference this time around is that instead of using the TI calculator, I decided to use an online platform instead that everybody should know about at this point, which is Desmos.com, simply because a lot of people don't have the TI calculators available when they need them, whereas the browser is always available. So if you're going to be doing this with a browser, this makes the most sense to me. And so I elected to create a new set of videos. So first thing, where is Desmos.com? Desmos.com is located, as you might guess, at desmos.com. It's a good idea to log in, and that way you can save your files. So I recommend that highly. And also, I think it's a good idea to think about this in terms of templates. Create templates for each problem so that you can just reuse the templates as you need them. So let's get started with this one. Homework 16, Applications of Quadratic Functions. There are 7 problems, 7 points available. And number 1, this is the blood pressure problem. A person's systolic blood pressure, which is measured in millimeters of mercury. Long story short, this is blood pressure given a person's age. That'll stand in for Y. And then the P is the person's age. Blood pressure given the person's age. So we're going to transfer this entire equation into Desmos.com exactly the way you see it, with one major difference. You shouldn't worry about it. Basically, you have to change the y's to x's because Desmos will only take it as y is equal to something x squared so far. Otherwise, it's the same equation. And since this is the template, I just have to change specific numbers. So the 119 becomes the 120. Everything else looks like it's the same. And that would be all you really need to do. It's really that simple. When you go to the graph, you're not seeing the graph right now because it's not visible, but if I click that, you'll see it. You can see that it's a positive parabolic curve. It's got a minimum, and then it goes up from there. So you just have to answer the question now. Now, given the age of a person being 41 years old, it's basically asking what happens to P, or in this case Y, when X is 41. So you do an in and out table, it'll give you the answer right away. I'm going to show you how to do that. What you need to do is you go to the gear icon, then you duplicate the function, and then change that into an in and out table. And you get about 5 entries when you do that, but you don't need any of them. You really only need the one line, which is what happens when X is 41. So if you type 41 there, you'll get your answer right away. And that's the answer you're going to put into your Desmos when you do it. So that equates to right about there. You can see it's the same value, 130.947. And I like to give the answers 2 digits just because it seems like there's less problems when I do that. 130.95 in this case. The second question is reversing it. What happens when you know the pressure and you want to find out the person's age? And this is actually pretty cool because normally you would have to do a little algebraic manipulation, subtracting to get 0. Remember, solving an equation means to set it equal to 0 and figuring out what values will give you that. But with Desmos, you don't need to do that, which makes it much easier. All you need to do is note that the goal you're looking for is to figure out where is 135.83 along the curve. And for that, you just need to type in the equation y equals 135.83, system of equations concept, basically. And you'll see that there's an intersection when you've got 2 intersections here, actually. You've got the gray balls there, dots. You've got one at 49.005. You also have one that's negative, but that doesn't make sense, right? That's a negative age. It makes no sense. So the age is actually going to be 49 years old, it looks like. So that's what you're going to put into Lumen as the answer to this particular problem. And I think you'll agree that this is much easier than using any other type of calculator. Desmos is your best friend. We're going to put 49 in here and hit enter. And we got it right. So I think this is our best approach. Question number 2, you can see it took one decimal place. I like to give it 2 just because it can get a little pain sometimes. Next one. This is an area problem involving a box with a square base with no top, and you're going to make a box with a volume of 9,408 cubic inches. How big a piece of cardboard do you need to do? It's good for this type of problem to visualize what you're doing. So what I like to do is show you what this problem is talking about. If you do a rectangle, you just have to draw something like that, maybe, and then another piece like this, and you can see that it's kind of a box, a piece of cardboard. I mean, that was corners were cut out, and the corners that it lost were 3 inches each. I like to put those there just to remember that that's going to happen. Now remember that the center part is a square, which means that the dimensions are the same for length and width. And we know that the volume, which is area times height, is 9,408 cubic inches. We know it's length times width times height, but I like to combine length times width and just call it area times height for volume. And that's going to be side times side, or side to the second power. So it's a square root problem at heart. If you set it up now, you can do the problem. That's going to be the area times the height is equal to 9,408 cubic inches. And we know the height is 3, right? Because if we fold it up, it'll be 3 inches high. So we're going to put that in. And then we're going to have to divide out the 3 from both sides. If we do that, we're going to get our dimensions for this box, which is 3,136 square inches. 3,136 is a perfect square. The only question is, what perfect square is that? So you got to do the square root of 3,136, or as we will find out later, 3,136 to the 1/2 power. It's the same thing as doing square root. And you see that it's going to be 56. So 56 makes up the side of the box, and you might put that down as the answer, but you would be wrong to do that, because you have to remember that it's from a complete piece of cardboard that was in the center 56, but it extended 3 inches in either direction. So you have to take into account that those extra 6 inches are required as well. So the entire box was 56 plus 6, or 62 by 62. That's your dimensions, and that's what you're going to want to put into your answers. If you do this wrong, that's why you're doing it wrong. So it's going to be 62 by, I didn't see that back there, it's blocked off by my writing. So 62 and then 62, and hit enter. I think we're ready. We got that right. I hope you find out, agree with me that that was an easy problem to do as well. Now, let's hit problem number 3. This is going to be a projectile problem, simple physics problem. You see them in every physics textbook in the world, and it's about a ball thrown by a child. The child is a few feet tall. It'll leave the child's hand at 5 feet, and it's got a gravity acting on it. That's the first term. And the initial speed that the child threw it is the second term. And it wants to know a couple things. It wants to know how high is the ball when it leaves the child's hand, and that's easy. In other words, what happens when x is equal to 0? But if x is equal to 0, the first 2 terms are going to drop out, and that's going to make it very simple to solve. But again, if you're not sure, you can always go to Desmos. And again, it's a good idea to set up another template for this kind of problem, so you can just change the values, the specific values, when you need them. So 1/16 became 1/14 for some reason. 2 is still the same. 5 is still the same. We don't see the graph because it's invisible right now, but you see that it's a little small curve. And sometimes you want to see it better so you can do what we need to do. So what I'm going to show you is that if you hit the shift key on your keyboard and you stretch along the y and x axis, you can stretch out the graph. And that's a really nice trick to learn because it'll help you a lot. You can fill the entire screen. I'm going to pull up until you get a nice manageable curve. You can see it, you can do with it, and it wants to know what happens when it leaves a child's hand. But again, like we said, that answer is 5. So that's an easy question. It really doesn't require a whole lot of work at all. And then the second one, what is the maximum height? Well, if you drag along the curve, it'll pause and max out at a certain point. That's going to be your maximum curve. In this case, it looks like it's 19 feet. All right. So when it's 14 feet across, it'll be 19 feet high. So that's what you're going to put into the second box. It's 19 feet. And then how far away from the child when the ball hits the ground? In other words, when is y equal to 0? And y is equal to 0 at 30.31 horizontal feet away. That's what that graph is saying. So we're going to put that in as well. And I'd like to put the decimal places since I have the space for it. I just have to make sure I'm typing it correctly. Hit enter, and we got that right. I'm sure you'll agree this is easy. Much better than using it with a calculator. We have another projectile problem here. Same exact kind of a problem, except that it's 32 foot high. A ball thrown vertically upward, and instead of horizontal distance, we have time as a variable. What happens with t is a certain number of seconds. So we're going to hit the next template I have for this. That's going to be negative 16. That's gravity. That never changes pretty much. X squared plus, change the details, to 56. Yep. Instead of 5, 32. And this is a graph, so we're not going to be able to do much at that look, so we're going to stretch it up. I mean, you might be able to do it, but I just like filling it up anyway since I'm here. And you get to see the entire thing that way. And now the question will be, what is the maximum height? The maximum height, again, if you drag along the curve, it'll stop at that maximum height, in which case it looks like it's 81 feet exactly. That's an easy one to put in, so we're going to give it 81. And then for the second question, how many seconds does it take until it hits the ground? In other words, where's it 0? It looks like it's 4 seconds later. So we're going to put 4. This is an easy problem. They're pretty much standard at this point. We got that right. Number 5. Okay, yet another projectile problem. This is a rocket this time, and it's got metric system instead of imperial system. So instead of negative 16, it's negative 4.9. Apart from that, it's the same. So if you go to the correct template, which will have negative 4.9, just have to put in the details that make it different. 208x, and what's the value for the c? I forgot. Let me look at it. 248. So we're going to put 248 there. And again, you're not going to see the graph until I make it visible, but if you do, now you can see the opposite problem. It's too big. Okay, that's not any better than the other one. So we're going to use the shift and drag approach to shrink the curve down so we can see the entire thing. We're going to pull it down, and we're there. That's pretty much all we needed. Okay, it wants to know when it splashes down. In other words, where is the graph going to be equal to 0? Where is y going to be equal to 0? And it's going to do right here, and that's going to look like 43.61 seconds. X is seconds, so we're going to put that down. And then where does it max out? What's the maximum height? It peaks at a certain height. The height is up there, and it's going to be 2,455.347. And I guess I could round that off to 0.35. So that's what I'm going to do here. And you're going to probably get that working correctly. Okay, so far so good. Number 6, we have 2 left. Okay, another projectile. Okay, we're going to go back to the negative 16 template. So we're going to look for that one again. And now we just have to change our values, which is why this is much easier this way. So I'm going to change the things to 183 from currently 130 and 8 from 7. So I'm going to make that change here, 183. And make this 8. 8, okay. And the curve is now visible, a little bit too big, so we're going to shrink it. Don't forget the shift key and dragging with the mouse and get it into a manageable shape. Okay, you're good. The question is, what's the height going to be at 487 feet? That's a tricky question, so I want to do that second. Let's do the last one primarily. When will it reach the ground? Well, we know where to go for that now. So we're going to move to here. We're going to get it at 0, and it's going to be 11.481 seconds. And this is the important part here. You have to select the correct units. 11.46 seconds. Seconds is your unit. I typed 46. I need to change that to 48. And otherwise, it should be okay. And it wants to know what will the height be at 487 feet. This is the problem. There's 2 places where that takes place. Okay, on the way up and also on the way down. Right around here, but also right around there. So you need to give it 2 answers. Easy way to find it. Just ask the Desmos, when is y, I have to clear up some memory, when is y equal to 487? And you'll see that they intersect at 2 places. Those are times. So the first one would be 4.1 seconds, I guess, 4.1 seconds, or 06 if you want to be careful, double digits. and the other one would be 7.38 seconds. And make sure you pick the correct unit. That's important. And now you're ready to go. These are absolutely correct. And this is super easy at this point. It's much easier than doing the TI calculator. Nothing against the TI calculator, but this is a lot easier to do. Now we have a gardener, we have fencing, there's a river, so we're going to create a rectangular pen, but we're not going to use the fourth wall because the fourth wall will be the riverbank. So we're going to use only the two sides and the bottom for fencing, and the fencing that we're given here is 1,160 feet of fence. This one's going to copy into a whiteboard so I can show you what we're going to do with this kind of problem. These are easy though. You just have to remember about area and length times width. And I'm going to make some space for it here. Let's see. Nope, not here. I'm going to go somewhere else. Up here. I'm going to paste it in. Now, again, think about the problem conceptually. It's going to be simply that we're not going to use all four sides, only 3 out of the 4. And a rectangle has equal dimensions on left and right, and the bottom is the bottom. But we know we have a total of 1,160 feet. Now, if we think about that, that means that of the 2, we're not using that one, but we are using the 2 sides on the bottom. And we're going to separate out. We're going to call that 1160 minus x on the left minus x on the right for the total number of feet being used here. And that's going to simplify, obviously, to 1160 minus 2x. That's going to be the bottom of the box. So this will be x. If this is x, then the part in the bottom must be 1160 minus the 2 x's for a total of 1160. That's part 1. Part 2, what is area? Area is length times width. So in this case, you would just multiply the length times the width, which is 1160 minus 2x multiplied by x. When you do that, what ends up happening is you get a quadratic equation. You get 1160x minus 2x squared. And it wants to know what the maximum area would be given that formula, and also what the dimensions of x and the other one are. And that's easy to do. Just remember that the maximum happens at the axis of symmetry, or negative b over 2a. You can solve it algebraically if you want to, or you can go once again to Desmos. And again, Desmos is your friend because you can do it there too. So that's what I'm going to do. And I'm going to find my template for that one. Template is, yeah, this is it. Although I changed the order a little bit, it is correct. And just remember the formula is 1160x minus 2x squared. You can totally do this algebraically, but since you're here anyway, we're going to type that in. Okay, it's going to be 1160x minus 2x squared. I don't need the second line. It was for something else, so I'm going to get rid of that line. Okay, we have a big, fat, flat graph. Doesn't help us see it, so we're going to drag it until we can see it. It will be a quadratic. You can see that it happened. We're going to pull it up a little bit so we can see that that happens too. And the maximum will be at the very top of the curve. It's a maximization problem, is what they call that. Okay, quadratics are either maximization, minimization problems, or they're where the values are equal to 0. This is a max problem. That happens when the x is equal to 290 feet, and the area you get is 168,200. So we're going to use both of those things. That means that this would be 290, and the other side would be 290. And what you'll find is that the bottom will be double that. Always. It tends to work out that way. So 1160 minus 290 minus 290 is 1160 minus 580, which again is 580, which makes sense. So those are your dimensions. You get 290 by 580. 290 by 580 is what we're going to put into Desmos, lumen right now. So the shorter side will be the 290. The longer side will be the 580. And then the area is the y value at that curve, which was 168,200. We're going to put that in that way, exactly in that way. 200. Hit the green button, hit the blue button. We got it green. We got all those right, and I think in fairly record time, I think you'll agree. So that's how you do this set of problems. I'm going to do another video for the quiz, but I think that's okay for right now. I'll talk to you, and watch out for the other video. All right, good luck.